So now let's try to understand a few of the phenomena that we've talked about, like relativity of simultaneity, relativity of lengths, and relativity of time intervals, as seen by different observers who are in a state of relative motion with respect to each other. And we will see these phenomena once again using our new tool of space-time diagrams. So let's start by trying to understand the relativity of simultaneity from the point of view of these space-time diagrams. So let's consider two events which, according to an observer S, where our observer S has this time axis and this x-axis. And let's consider two events which have the same time coordinate according to an observer in the frame S. So if we take these 2 points over here, these 2 points appear to have, these two space-time points, if I want to locate their time coordinate, I would draw a line passing through these points. Let's call this event 1 and event 2. I would draw a line passing through these points parallel through the x-axis to locate their time coordinates. So that line would look something like this. It passes through E1 and it's parallel to the x-axis, but the same line also passes through E2 and is parallel to the x-axis. So both these points lie on the same line of constant t. Okay, so that is both events E1 and E2 are simultaneous as seen by an observer in frame S. Are simultaneous in frame S. Now we would like to know, do observers in the frame S prime perceive them to be non-simultaneous? So to locate their time coordinates according to observers in the frame S prime, what we would need to do is we would need to draw grid lines which are parallel to the x prime axis, and passing through the points E1 and E2 respectively. So we draw two different lines. So let's draw those lines. So I've drawn the lines over here. This line is parallel to the x prime axis and it passes through the point E1. This line is parallel to the x prime axis and it passes through the point E2. And now you see that these lines intersect the t prime axis at different points, which means the t prime coordinates of events E1 and E2 are not the same. Or in other words, we can say E1 and E2 are not simultaneous in frame prime. Okay. How about two events now which are simultaneous in frame S prime? So let's try to identify those. So let me erase the previous grid lines. So let's take 2 points which have the same t prime coordinate. So one way to easily do that is let's draw a line which is parallel to the x prime axis. So let me just draw that line. And all points on this line have the same t prime coordinate. So if, in particular, if we take 2 points over here, let's say here and here, then these 2 points, which we can denote as E3, event 3 and event 4, they would have the same t prime coordinate. So E3 and E4 would appear to be simultaneous. To observers in S prime. But now what would an observer or the frame S conclude about events E3 and E4? Well, that's easy to see. What we do is, again, we draw grid lines which are parallel to the x-axis, which pass through the points E3 and E4. So here are those grid lines. And you can see that they are not the same grid line, okay, which means that they intersect the time axis of the frame S at different time points. And therefore, the points E3 and E4 do not have the same time coordinate according to observers in frame S. So E3, E4 are non-simultaneous events in the frame S. And now let's discuss length contraction from the point of view of these space-time diagrams. So before we discuss length contraction, let me just remind you how we choose our units along the x and t axis. So let's suppose these are our units, so these are equidistant. This is from 1 to 2, 2 to 3. And similarly along the x prime axis, we have a unit distance, but that unit distance, if you remember, was constructed using the hyperbola, the unit hyperbola that passes through the point x is equal to 1, t is equal to 0. So on our Euclidean diagram, okay, this diagram which is on a paper, this length is actually longer than 1 unit, okay, that is our reference over here. But this unit of 1 refers to a length of 1 meter as seen in the frame S prime. Okay, so now let's imagine that we have a rod placed with two endpoints. So let's say placed over here between the endpoints 2 and 3. So let me just draw that again. So let's suppose that we have a rod placed over here, and this rod is at rest in the frame S. Okay, so if we want to measure the length of the rod in frame S, we would locate one endpoint and then the other endpoint at the same instant of time in frame S. So in this case, this is at t is equal to 0, and we would measure the length of the rod. Now, if the rod continues to remain at rest in frame S, then for all future instants of time, we would have that, so if we draw the endpoints of this rod, if it continues to remain at rest, the endpoints of this rod at a future instant of time would look like this. Okay, so the rod would continue to have a rest length of 1 unit or 1 meter. Let's assume that we're measuring x in meters. So it would continue to have this unit length throughout. Okay, and so we could draw the world line of one end of the rod and the world line of one end of the rod, which is all the space-time points that this end of the rod passes through, would look like this. Okay, it just stays at the same x coordinate, but its t coordinate changes. And similarly, if we locate the other end of the rod and we ask what its world line would look like, that world line would look like this. Okay, it would stay at the same x coordinate but have a changing t coordinate. So for any future instant of time, if we locate the endpoints of this rod, the length of the rod would always be the same. It would be 1 meter as seen in the frame S. Now what we'd like to do is understand what an observer in frame S prime would measure the length of this rod to be. So let's suppose that the observer in S prime chooses to measure one end of the rod at, let's say, this instant of time. Now, what the observer in S prime needs to do is to locate the other end of this rod at the same instant of time according to them. And remember that a simultaneous measurement, as seen in frame S, which would be to identify this time, this point in space and time of the other end of the rod, would not be a simultaneous measurement according to observers in frame S prime. So for an observer in frame S prime, they would first have to decide what time they are measuring this endpoint of the rod, And we know how to do that. Let's draw a grid line which passes through this point and is parallel to the x prime axis. So that would be this grid line over here. And now what you would do is you would say that all points on this line have the same value of t prime. That is, if the value here at this endpoint is ta prime, the value here is tb prime. Okay, so using this, we are now able to identify the we are able to do a simultaneous measurement of the endpoints of the rod. TB prime is the same as TA prime because they lie on the same grid line of constant T prime. And so now we're able, according to observers in frame S prime, we're able to locate the endpoints of the rod simultaneously. It's just that this location in space and time is not a simultaneous measurement according to observers in frame S. Now, having located these two endpoints, we now need to find their x prime coordinates and take the difference between them to find the length of the rod as measured in frame S prime. So the way to do that is, again, through the point A and through the point B, we draw grid lines, but this time we draw the grid lines parallel to the T prime axes. So this is what those two grid lines look like. And so now we can, all these points on this line here have the same x prime coordinate, and all the points on this line have the same x prime coordinate. So we locate where they intersect our x prime axis, and this gives us the location x prime A, and this gives us the location x prime B. And the thing to remember is that a unit length along the x prime axis is this amount, okay, this amount. So now if we use this to identify x prime A and x prime B, we would say something like x prime A, let's say, is 1.2 units, and x prime B is, let's say, 2 units, okay. So this is 2 units away from x prime is equal to 0. So the length x prime B minus x prime A would be something like 2 minus 1.2, which this is just examples, which I'm just making up. But you could imagine that that length would be something like 0.8. So the length as measured in the frame S prime would be smaller than the length as measured in frame S, which would be 1 meter, okay? Where the observer in frame S located them simultaneously at the points XA, XB, and said that the length was 1 meter. But the observer in S prime said that the length was 0.8 meters. So the observer in frame S prime would conclude that the rod appears to be shorter because the rod appears to be moving with respect to them, okay, moving with a velocity minus beta, since S is moving with a velocity minus beta with respect to S prime. Similarly, I won't draw this, but you can convince yourself that a rod at rest in the frame S prime would appear to be shorter as seen by an observer in frame S. Okay, so I urge you to do this as an exercise, is to draw the whirl lines of the endpoints of a rod which are at rest in the frame S prime, and then see what an observer S would conclude about the length of that rod. And the key point to remember is that observer S has to measure the endpoints of the rod by locating them at the same instant of time according to themselves. And that locating them at the same instant of time according to themselves is not simultaneous according to observers in frame S prime. Okay, so therefore we conclude that moving rods appear to be shorter. or this is the phenomena of length contraction. And finally, let's discuss the idea of time dilation from the point of view of these space-time diagrams. So again, the x and ct axis represent what an observer in frame S would conclude about the coordinates of any space-time point, and the axes x prime and ct prime tell us about the coordinates of an observer in frame S prime moving with respect to S at a speed beta. Now, again, recall that if I take a unit time along the t-axis, the length of this unit time is different from the length of the unit time as measured along the ct prime axis, because to get that unit length, we would again have to draw the unit hyperbola passing through the point, this point, and so that unit length in time for the ct prime axis would lie somewhere here. So on our sheet of paper, this would be longer than the length here of 1 meter, or let's say 1 light second. Okay, now this time to understand time dilation, what we'll do is let's consider a clock which is at rest in the frame S prime. So this clock could be located at any x prime. So let's consider a clock which is located over here. And let's draw the whirl line of this clock. So if we draw the whirl line of this clock, it would be at rest. So it has to maintain a constant x prime, which means we need to draw a line which passes through this point over here and which is parallel to the t prime axis. So I've now drawn this whirl line for the clock at location x prime. And you can see that this whirl line is parallel to the ct prime axis, which indicates that this clock has a fixed value of x prime. So in frame S prime, this is a stationary clock. And now suppose we want to mark off a unit interval of time along for the stationary clock. Now what we could do is take the point that we've identified over here as having a time t prime or ct prime of one unit, and we could draw a line which is parallel to the x prime axis. So let's draw that line. So this is a line passing through this point of unit time parallel to the x prime axis. Okay, so all points on this line have the same time, and you see where it intersects the whirl line of our clock, which was at location x, a particular location x prime. And therefore, since all points on this line have the same time, the time on this clock must now be 1 unit, okay, in the primed frame. So this corresponds to a time of t prime is 0. This corresponds to a time of t prime is 1 unit. So in our clock, which is in the moving frame, that is in the frame S prime, 1 unit of time has passed. Now what we'd like to do is we'd like to know how much time has passed on an observer S's clock with respect to whom this clock in the frame S prime is moving. So that's very simple to do. What we need to do is find the time of this space-time point and the time of this space-time point, and we need to measure what those times are. Okay, so that's fairly simple to do. What we need to do is we need to draw horizontal lines which pass through, let's denote these points as A and B. We need to draw horizontal lines passing through A and B and see where they intersect our time axis of the frame S and read off the times from there. Okay, so let's do that. So here I've shown horizontal lines that pass through the points A and B, and we can see now where they intersect the time axes. And what you can see from this figure is now we know what our unit length is along the time axis. So this is a unit of time as measured by observers in frame S. And you see that this time interval that has elapsed between the events A and B is longer than 1 unit. Okay, so therefore, the time that has elapsed in the frame S is going to be longer than the time that has elapsed in the frame S prime. Okay, and if you work out exactly what this is, delta t will be equal to delta t prime gamma. So what that tells you is that the time that has elapsed in the in the frame S with respect to which this clock is moving is longer, or that you have experienced time dilation. Okay, so this is the phenomena of time dilation. That is, the moving clock appears to run slower as timed by clocks which are with respect to which this clock is moving. Now, once again, you can construct a similar argument for a clock which is stationary in the frame S, and you could show that in the frame S prime, if I time that clock in frame S would be appearing to run slowly as or slower than compared to the clocks in frame S prime. Okay, so what you would have to do is consider the whirl line of a single clock in the frame S and see what intervals of time pass in the frame S prime when 1 unit of time passes on that clock. Okay, so again, I urge you to do this as a homework exercise to check on a space-time diagram, time dilation of a clock which is at rest in frame S.